Hello friends, I welcome you all to this class. This is linear algebra class, and in this class we'll be solving this question under this topic, diagonalizable matrices. Now, in our previous video we said that a particular square matrix A is said to be diagonalizable if you can find an invertible square matrix P and a diagonal matrix D such that this diagonal matrix D will be equal to P inverse AP. So if you find an invertible matrix P, an invertible square matrix P, so that P inverse multiplied by A multiplied by P will give you a diagonal matrix D, then this matrix A will be said to be diagonalizable. So this simply implies that what? If you solve this equation, it implies that your matrix A will be equal to P D P inverse. P inverse. So this will be what will give you then your matrix A will be equal to this. So all these things simply means that your matrix A will be similar to a diagonal matrix D. So in that, we want to use similarity and eigenvalues of this matrix A given to us on the board to evaluate A raised to power 10. So because matrix A will be equal to P D P inverse, so we need to get this matrix P, this invertible square matrix P. To get it, you have to compute the eigenvalues of this matrix A, then get the corresponding eigenvectors. Then when you get the corresponding eigenvectors, the eigenvectors will form the column of this matrix P. And when you have done that, you can write A to be equal to P D P inverse. What is this D? The diagonal matrix. Diagonal matrix will be formed by the eigenvalues. We will form it. So when we compute the eigenvalues quickly, we will use it to form this diagonal matrix D. Then we'll compute the corresponding eigenvectors so that we can get this matrix P. And with that, we write it as this. So A raised to power 10 will be equal to P D P inverse all raised to power 10. So this is what we'll do. So let's start the class. Solution. So to get the eigenvalues, you compute determinant of A minus lambda I, equate it to 0. So this implies determinant of your matrix A is given to you on the board. So this is your matrix A. Then minus lambda is a scalar. Then I is an n by n identity matrix. Since your matrix A is 2 by 2, it will be 2 by 2 identity matrix. So determinant equated to 0. So this implies determinant of, let's write our matrix A first. This is our matrix A minus, let's use lambda to multiply the identity matrix. Lambda multiplied by 1 is lambda, lambda multiplied by 0 is 0, lambda multiplied by 0 is 0, lambda multiplied by 1 is lambda. Then we have determinant equated to 0. This implies we can subtract, right? Negative 1 minus lambda, we have negative 1 minus lambda. 2 minus 0, we have 2. 2 minus 0, we have 2. Then negative 1 minus lambda, we have negative 1 minus lambda. Determinant equated to 0. So this simply implies, so we have a 2 by 2 matrix to compute determinant. So what we are going to do is simply you multiply what the entries of the principal diagonal. What's the entry? This and this. So I'm going to multiply negative 1 minus lambda multiplied by what? Multiplied by negative 1 minus lambda. Right, we have done it. Then you subtract the product of the other diagonal. That's 2 multiplied by 2 is 4. Equate it to 0. So we can expand, right? Negative 1 multiplied by negative 1, I have positive 1. Negative 1 multiplied by negative lambda, I have positive lambda. Negative lambda multiplied by negative 1, we have positive lambda. Negative lambda multiplied by negative lambda, we have positive lambda squared. Then minus 4 equated to 0. So we write this lambda square first. Lambda squared. Lambda plus lambda, we have positive 2 lambda. 1 minus 4, we have negative 3. And equated to 0. So this is a quadratic equation we can factorize. So the constant here we have here is negative 3. Multiply it by the coefficient of lambda with the highest power, that's lambda raised to power 2. What's the coefficient? 1. Negative 3 multiplied by 1 is negative 3. So we need the two factors of this negative 3 such that their sum will give us the coefficient of this lambda at the middle, that's lambda power 1. So what's the coefficient? Positive 2. So we need the two factors of this negative 3 such that the sum will give us positive 2 and the product will give us negative 3. So positive 3 plus negative 1 will give us what? Positive 3 plus negative 1 will give us what? Positive 2, because we'll be doing 3 minus 1, which will give us positive 2. So we are going to get this positive 2 here. Then if you do positive 3 multiplied by negative 1, you are going to get this negative 3, right? So with that, we have gotten what will replace this 2 lambda. So the first lambda will have the coefficient 3, and the second lambda will have coefficient negative 1. So 2 lambda is same thing as 3 lambda minus lambda. So this implies lambda raised to power 2 plus 3 lambda minus lambda, then minus 3 equated to 0. So with this we can factorize. So this simply implies lambda, we have common factor at lambda. Lambda divide lambda square, we have lambda, plus lambda divide 3 lambda, we have 3. Then what is common here? What is common here is negative 1. Factor out negative 1, so we have positive lambda, we have positive 3, and equated to 0. So this implies, so we have peak lambda, negative lambda, peak lambda and negative 1, we have lambda minus 1. Then pick one of these, lambda plus 3, equated to 0. So this implies that lambda minus 1 equals 0, or lambda plus 3 equals 0, because the product of these two quantities are giving us 0. Is either that this is 0 or this is 0, right? So if you solve, this implies that our lambda 1 will be, move this negative 1 to the right, you have what? Positive 1, and our lambda 2 will be equal to, move this positive 3 to the right, we have negative 3. So lambda 1 will be positive 1 and lambda 2 will be negative 3. So we are going to find let's find the eigenvectors corresponding to each of the lambda. So for you to get the eigenvector corresponding to lambda equals 1, you solve this equation. A minus lambda sub 1 I multiplied by capital X equated to 0. So this is what the equation you are going to solve. So this capital X here is the eigenvector you are looking for. So this implies your matrix A, you write it negative, the answer is negative 1, 2, 2, negative 1. So this is our matrix A. Then minus, what is your lambda 1? Your lambda 1 is positive 1. That's what we got. So positive 1 multiplied by the identity matrix I, will have our identity matrix I. And what's this identity matrix? It is 2 by 2 because our matrix A is 2 by 2. That's 2 by 2 identity matrix. And 0, 1. Then your X is the column vector x1, x2. It will stop at x2 because you know your matrix A is 2 by 2. So how many rows? 2 rows. So we need just x1, x2. If your matrix A is 3 by 3, it will be x1, x2, x3. So we equated to this 0 will be the 0 column 0 matrix. So this is what we have. So with that we can proceed. So this implies, so let's subtract negative 1 minus 1 will be what? Negative 2. Then 2 minus 0 is 2. 2 minus 0 is 2. Negative 1 minus 1 will be what? Negative 2. then our vector x1, x2, our vector having entry x1, x2 equals, we have the zero matrix. So this is what we have. So we are going to perform a roll operation on this matrix. So we need to reduce it. So let's just reduce this so that we can solve this equation. Now we can reduce this matrix. Let's write it. To reduce it, we need to, that's to simplify it. So what is the first non-zero number in the first row? This -2. So let's make it to be +1. How do you make it to be +1? Multiply it by negative of the reciprocal of 2, so that it will be +1. So, and that's row 1. Row 1 will multiply by -half. If you multiply this by -half, this will be +1. So we have +1, and this will be -1. Right? We have done that. Then after what is below this number, this first non-zero number. The first non-zero number in a row is called the leading entry of that row. So the leading entry of this row, of this very quantity, is this -2, and what is below it is +2. What is below it, all the entries that are below it must be 0. So this 2 needs to be 0. So for us to make it to be 0, we have to add this row 1 to this row 2, because -2 plus +2 will give us 0. So you are, in other words, this is the same thing as multiplying row 1 by +1. We are multiplying by +1 because we don't want it to change. We want it to be the same row 1, so we can add it to row 2. So multiply by this thing I wrote is row, you multiply row 1 by +1, then add the result to row 2. That's this thing I wrote. So let's do that. +1 multiplied by -2 is -2 plus 2 is 0. +1 multiplied by +2 is 2. Adding it to -2 gets 0. So this is what we have. So with this, we have reduced this matrix. Right? We have reduced it. So we will have, so our equation now, we substitute this back in this equation. You are going to get this. So I'm replacing this matrix with the reduced form. So this is what we have. Now the next step, what I'm going to do next is to check whether each column have a leading entry of a row. The leading entry, that's it. After the reduction, the leading entry we have now after the reduction is +1. So the leading entry of this first row is this +1. That's the first non-zero number. Then it's located at what? Column 1. You know x1 is for column 1, x2 is for column 2. So since it's located at column 1 and x1 is for column 1, so x1 cannot be a free variable. So we cannot call it a constant. Let me say alpha. And if you look at this row 2, they are all zeros. So because they are all zeros, it doesn't have a non-zero number. Because of that, row 2 does not have a leading entry. And this makes this column 2 not to have a leading entry of any row, because it doesn't have a leading entry of the first row, it doesn't have a leading entry of the second row. So, and x2 is corresponding to column 2, so x2 will be a free variable. So let x2 be equal to alpha. It will be element of real numbers because your matrix A has entries of real numbers. So you will say this is what? Free variable. So because of that, we can proceed and solve the equation. We start from the last row. So use this to multiply the last row. x1 multiplied by 0 is 0, plus x2 multiplied by 0 is 0. That's 0 plus 0 equal to what? 0. Did we get any value for x1 and x2? The answer is no. So we'll go to row 1. x1 multiplied by 1, we have x1. x2 multiplied by negative 1, we have negative x2 equated to what? 0. So if you solve for x1, x1 will be equal to, move negative x2 to the right, we have positive x2. So, and which implies that x1 will be equal to alpha, because x2 is alpha, right? So with that we have gotten the vector, our first vector corresponding to, that is the vector corresponding to the first term, lambda. That's lambda equals 1. And this will be equal to, what's our x1? Alpha. What's our x2? Alpha. So we can choose any alpha. We can choose any alpha because alpha is the element of real number. We can choose alpha. It's the simplest one. Let's choose alpha to be 1. Let's choose alpha to be 1. So this at alpha equals 1 for simplicity's sake. So with that, we have gotten the eigenvector corresponding to lambda 1. For lambda 2, which equals, what do we get for lambda 2? Negative 3, right? Which equals negative 3. We will solve. So we'll solve this equation. A minus lambda sub 2I multiplied by capital X equated to 0. So we'll solve this quickly, as we did for the lambda one. So this implies your matrix A is given to you on the board, so you can write it down. Then minus our lambda 2 is negative 3. So you are going to be doing negative. So negative with positive. So we have positive 3 I, and our I is the identity matrix. It is 2 by 2 because your matrix A is 2 by 2. Then this is what we have. Then we have this capital X to be, as we had it before, this column vector. Then 0, the 0 matrix. So this is what we have. So we can simplify, right? So this implies, so now we can write our matrix A. Then plus, let's multiply out. 3 multiplied by 1 is 3. 3 multiplied by 0 is 0. 3 multiplied by 0 is 0. 3 multiplied by 1 is 3. Then this is what we have. Then we have this vector, then equated to this 0 matrix. So we can add these two matrices, right? So let's add quickly. So negative 1 plus positive 3 is what? Positive 2. And 2 plus 0 is 2. And 2 plus 0 is 2. And negative 1 plus positive 3 is 2. So we have this. Then multiply by this vector equated to the 0 matrix. So this is what we have. So we can continue the solving this side. So as we did earlier, we are going to reduce this matrix. We are going to reduce this matrix. Now this matrix, so this matrix, we will reduce it by performing a roll operation on it. So let's perform roll operation. So the first non-zero number in this row is what? 2. So we are going to make it to be 1 for simplicity's sake. So let's make it to 1. How do we make it to 1? Multiply it by half. So row 1 multiply by half. So if you multiply this by half, what will you get? You get 1, 1. If you multiply row 1 by half, so you get 1, 1. Then after the first non-zero number, which is 2, and the 2 is located at column 1. So every other number below 2 at that column 1 will be what? 0. So what is below 2 is this 2 located at the second row. So let's make it to be 0. How do we make it to be 0? We know that this, if you multiply this positive 2 at row 1 by negative 1, if you add negative 2 and it will give you negative 2. If you add negative 2 and positive 2, you get 0. So let's do that. So we're going to do row 1. We multiply it by negative 1. and add the result to row 2. So negative 1 multiplied by row 1, add the result to row 2. So negative 1 multiplied by positive 2 is negative 2 plus positive. So negative 2 plus positive 2 gives 0. Negative 1 multiplied by positive 2, you get negative 2 plus positive. So negative 2 plus positive 2 gives 0. So this is what we have, right? So with this we have reduced this matrix. So because we have reduced it, we can now go and ahead and replace it for the former matrix we have. So let's go and replace it. So replace this with this. So we have this reduced matrix. So then we have the column vector, then equated to this 0 matrix. So this is basically what we have, and we need to solve this equation. So as we did there earlier, we check whether each of the column has a leading entry. The first column has a leading entry of the first row. That's the first non-zero in the first row after the reduction is 1. So x1, I told you x1 is for column 1, while x2 is for column 2. So x1 will not be a free variable, that's a constant. Then in row 2 has 0 throughout, so no leading entry, no non-zero number. So this makes this column, the second column 2, not to have a leading entry of any row. So column 2 does not have a leading entry of any row. So x2 is corresponding to column 2. Because of that, x2 will be a free variable because it's corresponding to column 2, and column 2 does not have a leading entry of any row. So we are going to call it a free variable alpha. Let x2 be equal to alpha, element of real numbers, and we say that it will be a free variable. Right? It will be a free variable. Then so if you do that, let's solve the equation. Start from the last row. X1 multiplied by 0 is 0, plus x2 multiplied by 0 is 0. 0 plus 0 will give you 0, equated to 0. Did you get any value for x1 and x2? The answer is no. Because of that, we go to row 1. So x1 multiplied by 1 is what? X1, plus x2 multiplied by 1 is x2, equated to what? 0. We have here. So if you make x1 subject to the formula, so x1 will be equal to, move positive x2 to the right, we have negative x2, which will be equal to, what is your x2? We have called it alpha, so it's negative alpha, right? X1 is negative alpha. So that our column vector having this entry x1, x2 will be equal to, what is x1 is negative alpha, what is x2 alpha. So it means that what we are going to get, what we get will determine by the alpha we choose. So let's choose the simplest alpha. Alpha is any real number because your matrix A has entries of real numbers. So we can choose the simplest alpha 1. So here will be negative 1, here will be positive 1. So at alpha equals what? 1. So with this, we have gotten the corresponding eigenvector. So matrix P will be formed by the first eigenvector for lambda equals 1. We got it to be this, right? This vector. So I have 1, 1. For lambda equals negative 3, this is what we got. This vector. This is what we got. So with this, we have gotten our matrix P, right? So the next thing we are going to do is we are going to get P inverse. Let's get P inverse. P inverse will be equal to, this is 2 by 2 matrix now, right? So to get the P inverse, let's first of all get determinant of P here. Determinant of P will be equal to, so let's evaluate the determinant. You multiply the principal diagonal. 1 multiplied by 1 is 1. You subtract the product of the other diagonal. 1 multiplied by negative 1 is negative 1. So you have negative, negative, that's positive. So you have what? 2. Right? We got 2 as the value for the determinant. So P inverse will be 1 the reciprocal of this determinant, 1 over this determinant, multiply by, so what you are going to do, you are going to interchange the position of the principal diagonal, interchange this and this, because they are the same thing. So interchanging it does not change anything, because it's just 1 1. So we interchange it, then we change the sign, of the other diagonal. So since this one is negative, it will be positive, and since this one is positive, this one will be negative. So this will give us the inverse of this P. So the next one we're going to do is to write our matrix A. Our matrix A now, your matrix A will be equal to, as I told you earlier, your A will be equal to P D P inverse. This will be your matrix A, P inverse. So A raised to power 10 will be equal to P D P inverse, all raised to power what? 10. This is what you are going to get. So this will be equal to P. This will be the same thing as PD. The power will be on this middle value, because this is just conjugate. This expression means you are conjugating D. So the power will be, this is P D raised to power 10 P inverse. So this is what this will give you, and this will be equal to P. What is your D? Your D is a diagonal matrix that will be formed by the eigenvalues lambda 1. Since our matrix A is 2 by 2, it will be 2 by 2, lambda 1, lambda 2, right? Then P inverse, then raised to power 10, because you are raising D to the power 10, right? So this simply implies, what is your matrix P? This is our matrix P, right? Then our D, before writing that, let's just simplify further. This will be P. Then this power, this is same thing as lambda 1 raised to power 10, lambda 2 raised to power 10. So the powers will be distributed on the entries of the principal diagonal of this diagonal matrix. So this is P inverse. So this is what we have. So this implies, what is our P? This matrix. So this is our P. Then what is the diagonal matrix? The diagonal matrix is it will be formed by the eigenvalues. What is our lambda 1? We got lambda 1 to be 1, right? So we're having 1 raised to power 10. 1 raised to power 10 is 1, right? So we have 0 here, we have 0 here. The other one we got was what? We got negative 3, right? Our lambda 2 raised to power 10, because we have lambda 1 raised to power 10, lambda 2 raised to power 10, right? So this is what we have. Then P inverse, this is what we got as our P inverse. So we have this constant here. So let's just multiply everything by this half. So we have half, negative half, and half. So this is what we have. So right, this is what we have. So we can multiply this first two products first. So this implies, so let's multiply it first. So we use this first row to multiply the first column. 1 multiplied by 1 is 1. Negative 1 multiplied by 0 is 0. So if you add the two results, you have 0. Sorry, you have 1. Sorry. Add the two results, you have 1. Then use the first row to multiply the second column. 1 multiplied by 0 is 0. Then negative 1 multiplied by this negative 3 all raised to power 10, because 10 is even. This is the same thing as 3 raised to the power 10, right? So by the time I multiply it by negative 1, I have negative 3 raised to the power 10. Right? This is what we are going to get. Then use the last row to multiply the first column. 1 multiplied by 1 is 1. 1 multiplied by 0 is 0. So if you add, you get 1. Use the last row to multiply the second column. 1 multiplied by 0 is 0. Right? Plus 1 multiplied by this quantity. I told you that this negative 3 all raised to the power 10. Since the power is even, it's same thing as positive 3 raised to the power 10. So 1 multiplied by this positive 3 raised to the power 10, you have the same thing, positive 3 raised to the power 10. Then this is what you have. Then multiply by this matrix half, half, negative half, half. So this is what we have. So we can finish up the solving this side, right? We can finish up the solving. So this simply implies, so we can multiply, use the first row to multiply the first column. 1 multiplied by half, you have half. Then negative 3 raised to the power 10 multiplied by negative half, you have positive half. Positive half multiplied by 3 raised to the power 10. 3 raised to the power 10. So this is what we are going to have, and we can write it here. This is half plus, we can write it as 3 raised to the power 10 half. That's the first entry. Then for the second entry, use the first row to multiply the second column. 1 multiplied by half is half. Then negative 3 raised to the power 10 multiplied by half, we have negative 3 raised to the power 10 divided by half. Divided by 2, sorry. So we have 1 half minus 3 raised to the power 10 divided by 2. So this is what we have. So this is what we have. Then the next one I'm going to have, use the last row to multiply the first column. 1 multiplied by half is half. And 3 plus, so half plus 3 raised to the power 10 multiplied by negative half. So I'm going to have negative 3 raised to the power 10 divided by 2. So I have half minus 3 raised to the power 10 divided by 2. So this is basically what we have. Then use the second row to multiply the last column. 1 multiplied by half is half, plus 3 raised to the power 10 multiplied by half. So we have 3 raised to the power 10 divided by 2. So half plus 3 raised to the power 10 divided by 2. So with this, we have gotten the result of this. So what is left is just to use calculator and do the computation. So thank you so much for being part of this class. See you in our next class.